Hello pre-cal students. Today we're going to be graphing our trig reciprocals to end out the rest of this unit. So we're going to start off by figuring out what the graphs of cosecant and secant look like. So those are the reciprocals of sine and cosine. So first, let's just graph the normal sine and normal cosine parent functions, and then we'll see how we can get the reciprocal graphs from these. So for sine and cosine, we know our midline is 1, our midline is 0, our amplitude is 1. Starting off at x equals 0, our sine wave has a period of 2 pi, so the step would be 2 pi over 4. Our step is going to be pi over 2 for a sine graph and for a cosine graph. So this would be 2 pi over 2, which is pi, 3 pi over 2, and then 4 pi over 2, which is 2 pi. And for sine, we know that starts at the midline, goes up, comes down, and there would be our sine graph. For cosine, our x and y axis are going to be the same as for sine. We just know that cosine starts at the maximum and ends at the maximum. So we would have max to max. Okay, so those are our parent functions of sine and cosine. Those are going to help us figure out what the graphs of cosecant and secant will look like. But this first question is kind of hinting at something. What will happen to the graph of secant at the x values where cosine equals 0? Well, remember, cosine, that's the reciprocal of secant. So if cosine is 0, well, what's the reciprocal of 0? Well, the reciprocal of 0 is undefined. Okay, so secant is going to be undefined at those x values. If secant is undefined there, then that means that secant will have some vertical asymptotes. So for anywhere that cosine has a point on the midline, right, at the 0, then that's going to end up being a vertical asymptote for the secant graph. Okay, so what will happen for secant? Secant will have vertical asymptotes anywhere that the cosine value is 0. All right, so here's what I found to be one of the easier ways to create the reciprocal graphs. I actually like to create the reciprocal graphs using the original sine and cosine waves. So if you look at the graph of sine, right, we're going to use that to create the graph of cosecant since they are reciprocals of each other. So if I was going to take the reciprocal of each point, right, of this parent function, well, if I took the reciprocal of 0, I would still get undefined, right? The reciprocal of 0 is undefined. So our cosecant graph is going to start off being undefined. So it's going to start off having a vertical asymptote. If I took the reciprocal of 1, well, the reciprocal of 1 is still 1. So I'm still going to have, I don't know why I keep zooming in and out like that, sorry. I'm still going to have a point up here at 1 because the reciprocal of 1 is 1. All right, continuing on. If I look at my next key point, right, my y value is 0. The reciprocal of 0 is undefined. So again, we're going to have a vertical asymptote for cosecant. Down here, we're at -1. The reciprocal of -1 is still -1. So we're still going to have a point right there at -1. And then the reciprocal of 0, again, is undefined. So we're going to have another vertical asymptote. So here's our key points for cosecant. But what does the graph actually look like? Well, how are we going to figure out, like, how do we approach the vertical asymptote? Are we getting closer to it like this, or like this, or like this? Let's figure that out. So remember, we just chose random key points. But if I looked at, like, for instance, this value right here, right? That could be at a value of, like, 1/2. If I took the reciprocal of 1/2, the reciprocal of that would be 2, right? So that would be something larger than 1. So the reciprocal of 1/2, that's 2. So that means this point would actually be higher than 1. It would be like up here, like at 2, right? And you can try that with anything, right? You could even try that with like anything between the y value of 0 and 1. Like let's say we picked, I don't know, let's say we picked something close to 1, like 9/10, right? 9/10, well, that would reciprocate and give us 10/9. That's a little bit larger than 1. So that point would be like right here. So if I reciprocated all those points, I can see that we're approaching the vertical asymptote pointed up towards positive infinity. If you continue that on the other side as well, again, same thing, right? We could pick a point with a y value right here. That y value would be a half. The reciprocal of a half is still 2, right? So we would reciprocate it and it would be above the y value of 1. So this is kind of creating the shape of our cosecant graph, right? We're just reciprocating each point. Let's look at this side of the graph too, on the other side of the vertical asymptote. Well, picking a random point on our sine graph, if I picked this point right here, right, that could have a y value of like negative a half. Well, the reciprocal of negative a half is negative 2, right? So this point right here at the same theta value is now going to be at negative 2, right? So we're approaching the vertical asymptote from this side of it, pointed down towards negative infinity. Trying just one more to show you. If I choose a point right here, the y value is negative a half. The reciprocal of negative half, again, is negative 2, so it's going to be a point right there. So connecting that, we can see how, that's supposed to be kind of a smooth curve. We can see how the cosecant graph is coming to shape, right? You have some vertical asymptotes. You have some arrows pointed up and down towards that. But essentially all we did was reciprocate each point, right? So we took the reciprocal of the 0, made it a vertical asymptote. We took the reciprocal of this, and it ended up reciprocating, or it looks kind of like a reflection, but it reciprocated all those points. We created a vertical asymptote. We reciprocated this point. We created a vertical asymptote. So if you just want to like kind of imagine like you're taking the reciprocal of each individual point, and that's going to create your reciprocal graph for cosecant. Now I should keep labeling this x-axis, right? The x-axis is going to stay the same. We still have those same theta values with the same step. So there would be the x-axis for cosecant. We're going to do the same process for cosine and secant, because again, secant is just the reciprocal of cosine. So if we make the same x and y axis, then we can just reciprocate each of the points. So looking at the first point for cosine, that's at a point of 1. Well, the reciprocal of 1 is still 1, so we're still going to have a point right there. Cosine is 0 here. Well, the reciprocal of 0 is undefined, so secant will have a vertical asymptote. Down here at negative 1, the reciprocal of negative 1 is still negative 1, so we're going to have a point still there. Reciprocal of 0 is undefined, so we're going to have a vertical asymptote. And then ending at 1, the reciprocal of 1 is still 1, so we're going to have a point right there. Now again, think about kind of flipping each of your points. Again, it kind of does look like a reflection, even though like it's not. Each of these points are getting reciprocated. So if I chose a random point right here that had a y value of, let's say, like 1/2, the reciprocal of that is 2. So the reciprocal of that would be like way up here. So we can see we're approaching this vertical asymptote pointed up. Same thing over here, same exercise. If I chose a y value down here, let's say at negative a half and negative a half over here, those are going to reciprocate, and now we have reciprocals of negative 2. So negative 2, negative 2. We can see the shape of this secant graph coming along. And then ending off this last little section, again, just choose a random point. Let's say this one right here at 1/2, the reciprocal of that is 2. So the reciprocal would be somewhere up here. We're pointed up towards our vertical asymptote here. So there's a period of secant and then cosecant over there as well. Now we're going to sketch a graph that has some type of transformations. So the way that I like to do something that has a lot of transformations is, honestly, I like to just graph the original graph, like the reciprocal, and then graph the reciprocal right on top of that. So if I have a graph of secant, I like to first make the graph of cosine, right? So the reciprocal graph would be 3 cosine of 2 pi over 5x. If I can create that graph for cosine, then I know that I can just take the reciprocal of each of those points. So for cosine, this would have a midline of 0. It has an amplitude going up 3 and down 3. It doesn't have a phase shift, so we're starting off at x equals 0. We do have a b value, so that's quite drastically going to change our period and step. So let's see. Since this is a cosine graph we're making, our period would be 2 pi over b. So the period is 2 pi over 5. The period would end up equaling 5. And if the period is 5, then the step is 5 over 4. The step would be like 1.25. So 1.25, actually I'm going to keep doing this in pink. So our step is 1.25. And we have our x-axis labeled. So if this was just a normal cosine graph, we would start at the top, go down, and there's our cosine graph like this. All right, but we know that we don't want the cosine graph, we want the secant graph. Honestly, I'm fine with if you just make the secant graph right on top of that, if you're putting it in like a different color or something, right? This is our cosine graph. The secant graph is going to reciprocate each of those points. So anytime we have a point on the midline, right, that had the original value of 0, that's going to turn into a vertical asymptote for secant, right? So I'll show you kind of over here what we're graphing. That's going to turn into a vertical asymptote at the x values of 1.25 and the x value of 3.75. So this is our graph of the secant one. That secant one. Okay, so now if we reciprocate our maxes and our mins, right, this is the maximum up here. If I would reciprocate the shape of this graph, it would end up pointing up. So for our secant graph, it's going to end up pointing up towards that vertical asymptote. If I was going to reciprocate this point and curve, then it would end up pointing down. So our graph is going to be reciprocated pointing down. And then again, this maximum is actually going to reciprocate and be a minimum for our reciprocal graph. So that's kind of doing the graph of the reciprocal. Again, you have the same key points, they just get reciprocated or turned into vertical asymptotes. And you're not like technically taking the reciprocal of 3 here. That 3 was supposed to be at 1, like as its original amplitude, so you would have reciprocated that, and then you would have amplified it by 3. All right, next we're going to find the domain of the cosecant graph. Again, if you're ever asked to like graph or do anything with reciprocal graphs, I think it's just easier to find the original graph first. So our original graph, the reciprocal of cosecant would be sine. So let's just graph the sine graph with all these transformations. All right, so sine graph, this one has a midline of 0, an amplitude of 1. We have a phase shift to the left by pi over 2, so we're starting at negative pi over 2. And then our b value is going to change the period of this sine wave. So our period is 2 pi over b. So if we do 2 pi over 1/3, we're going to get 2 pi times 3, which is 6 pi for the period. All right, so if the period is 6 pi, then let's figure out what the step is. Step would be 6 pi over 4, so that simplifies to 3 pi over 2 for our step. So if I start at negative pi over 2 and I step over by 3 pi over 2, now we are at 2 pi over 2, or just pi. And then stepping over again, we're at 5, 8, and 11 pi over 2. So those are our steps and our x-axes. Again, if we were doing sine, start at the midline, go up, midline, bottom, midline, and this would be our sine graph. I'm going to make our cosecant graph directly on top of that. Okay, so our cosecant graph, I'm going to do this one in green. We're, again, just reciprocating each point, right? So taking the reciprocal at 0 is going to turn into a vertical asymptote. Taking this reciprocal and reciprocating each point is going to turn the graph for cosecant like this. Vertical asymptote, take the reciprocal, and take the reciprocal. The graph's going to look like this. and ending with a vertical asymptote. So there's our graph for cosecant. The question is asking us to find the domain of this. So the domain is like all of our input values. So notice that the domain is all real numbers except any place that we have a vertical asymptote. So our domain here is going to be all real numbers except, and we need to put any places that we have the vertical asymptote. So except x equals, and the first vertical asymptote we have is right here at negative pi over 2. So except x equals negative pi over 2, and that's not the only one. We're going to have one every single half of a period, right? The next vertical asymptote is only 6 pi over 2 away. So that would be 3 pi away, right? You actually have a vertical asymptote every single half period. So plus 3 pi n, because we can see 3 pi later, that's when we have the next one. 3 pi later, that's when we have the next one. So plus 3 pi n, where n is an integer. That would be the domain of our cosecant graph. So you're essentially just excluding from the domain, you're excluding where you have vertical asymptotes. All right, now finding the range of the secant graph. Again, whenever you're graphing reciprocals, it's just easier to start off graphing the original reciprocal. So I'm going to graph right here. The reciprocal of secant is cosine. So we're going to graph a normal cosine graph with all these transformations. So we can see the midline is -5, the amplitude is 4. We shifted to the right by 3, and the period changes. The period is actually 1, so therefore the step is going to be 1/4, or 0.25. So 3.25, oh, I'm going to go back to pink. Just do it all in the same color. Okay, so there's our full cycle. If we're doing cosine, oops, cosine does not make a sine wave. Cosine starts at the maximum. So cosine starts at the max, goes down, and ends at the max. This would be our cosine graph. But again, our graph is actually asking us to look at the secant graph. So just reciprocate each of the points, right? If I took the reciprocal of this point, it's just going to reciprocate like this. If I took the reciprocal of this one, remember, it was originally at a midline of 0 before it got shifted down by 5. So if I would have taken the reciprocal of 0, I would have gotten an undefined and then just shifting it down by 5, but you can't really shift a vertical asymptote down by 5. Taking the reciprocal of this point, just kind of reciprocating each of those points would end up looking like this. Again, anything on the midline would have gotten reciprocated to undefined before it got shifted up or down, and then reciprocating this point. So now we have our graph of secant. Now we're going to find the range of this. So remember, the range is going to be like all your possible outputs or all your possible y values. So notice that we only have y values that are larger than -1 or equal to -1. And then we only have y values that are less than or equal to -9, right? We don't have any y values between -9 and -1, right? All of that is excluded from our range. We only have y values that are greater than or equal to -1, or any y values that are less than or equal to -9, right? Because we're graphing above this part, we're graphing below that part for secant. So this would be the range of our secant graph. Okay, and so moving on to this challenge question, I put challenge because I don't want you to like freak out about this question, but it is kind of cool, something to do on your own if you're interested in like what is so crazy about this question. So we have this function f, which is 3 cosecant of x, and then we have function g, which is 1 over that, so like the reciprocal of that. So again, anytime we're working with like reciprocal functions, I like to graph its original. So like if I'm working with cosecant, I want to graph the original sine graph for that, just to kind of see what we're starting off with. So sine graph, this one would have a midline of 0, an amplitude of 3, no phase shift, so same step, same period, same everything. So a sine wave, we would go middle, top, middle, bottom, middle, and there is our sine wave. But then what we have going on here is function f is the reciprocal of that, and then this new function g is the reciprocal of that. So function g is 1 over f of x. Well, f of x is 3 cosecant of x. Okay, so 1 over 3 cosecant of x. Well, we could think, oh, we can simplify that, right? Because 1 over cosecant, that's just sine. So we could just reciprocate that and get sine. But don't forget, we still have the 1/3. So it would be like 1/3 sine x, right? We're just replacing the 1 over cosecant. We're replacing that with sine, but we still got the 1/3, so we have 1/3. So that's this function g of x, okay? So function g of x is 1/3 sine x, but there is a catch, right? That's what's going to make this a challenge. If this is graphing 1/3 sine x, right, then our midline would be 0, our amplitude would be 1/3. We're not changing the period, so we still have the same normal x-axis. And then sine would go from the middle to the top to the middle to the bottom to the back to the middle, right? So this would be our sine graph. Now I am putting such like big open circles for a reason, because this is kind of what's making this a challenge. Yes, this simplifies down to like 1/3 sine x, but that's not what its original was, right? So think about like when we were doing like logs and exponent properties, like yes, you could rewrite them using some property, but that doesn't necessarily mean it was the original function. So 1/3 sine x was not my original function. That came from 1 over 3 cosecant x. So we actually have some domain exclusions because cosecant is not technically defined for all of its domain, right? If we go back to where we graphed cosecant is defined for all real numbers, but it doesn't exist at all at 0 or at pi or at 2 pi, right? So cosecant doesn't exist every single pi integer. So technically, before we simplified this, before we went from here to here, before we simplified it, cosecant is not technically defined, right? The domain for cosecant is not technically defined for every single pi integer, right? Every single pi n, where n is an integer. So technically on this graph, every single pi integer, we wouldn't have even been able to reciprocate. So this point needs to stay open. It would be a hole in the graph. This point needs to stay open, and this point needs to stay open. This one we can close in because that exists, right? That is in the domain of cosecant. But because 0 and pi and 2 pi are not in the domain of cosecant, then we wouldn't have been able to reciprocate those points in order to turn it into a sine graph. So this would be our answer to the question. So it's kind of a challenge because we end up having some holes in the graph. That's definitely not something that you need to worry about for like the test or anything in here. It's just kind of like a random difficult question in my opinion. And we're going to end this lesson by graphing our reciprocal of tangent. So we're going to make the cotangent graph. So again, the same way that we did the cosecant and the secant, we're going to start off by graphing the original function for tangent. Okay, so graphing our original function for tangent, we know it has a midline at 0, goes all the way up towards positive and negative infinity. We start at 0 and we get to actually graph 2 cycles of tangent here. Right, so 1 full cycle is pi, and then we actually have room to graph 2 full cycles of tangent on this window pane. Tangent starts at the midline, vertical asymptote, midline, vertical asymptote, midline, right? And then tangent is always increasing, so tangent is going to make a shape like this, bending, getting closer towards those vertical asymptotes. Where are the vertical asymptotes of tangent? Well, we can see the first one happens at pi over 2, but we're going to have one pi away, right? We're going to have 1 every single period. So plus pi n, where n is an integer. And we talked about this last class, so that shouldn't be astronomically new. We know how to graph tangent and where the vertical asymptotes are. But kind of a foreshadowing question. So what's going to happen with cotangent at the x values where I have vertical asymptotes on tangent? Well, if I have a vertical asymptote somewhere, that must have come from dividing by 0, right? For tangent, any place that we had a vertical asymptote, that's because we had like 1 divided by 0 or like -1 divided by 0, right? That's what created the vertical asymptote. But if I take the reciprocal of that, right, talking about cotangent, the reciprocal of that would be 0 over 1, which is 0. So actually for cotangent, anything that was originally a vertical asymptote will end up becoming a 0 or an x-intercept for cotangent, and vice versa. Anything that was an x-intercept for tangent will actually reciprocate and become undefined or a vertical asymptote for cotangent. So those are actually going to be zeros for a cotangent graph. Anything that was a vertical asymptote, the reciprocal of that would be 0. So the cotangent is going to be 0 there. So now let's sketch the graph of cotangent. Again, our axes are going to be labeled the same, right? We still have a midline at 0, still going up and down towards the infinities. And we're still going to have the same x-axis and same step, because we're going to be able to figure out how to graph 2 full cycles of cotangent as well. So graphing cotangent, again, if I took the reciprocal of my main points, well, the reciprocal of 0 is undefined. So cotangent is going to start off with a vertical asymptote here. The next key value of her tangent was a vertical asymptote, but if I take the reciprocal of that, it actually would have been a 0, so that actually is going to be a 0 for cotangent. Keep going on. The reciprocal of 0 is undefined, so cotangent is going to have undefined vertical asymptote. The reciprocal of a vertical asymptote came from a 0, so that's going to be a 0. And then last one, of course, is going to be a vertical asymptote for cotangent. Now, how would cotangent end up looking? The same way we did the sine and cosine, just pick like a random point. So if I would pick like a random point here, let's say that point was like, I don't know, let's say 1. Well, the reciprocal of 1 is still 1, so that point would still give me a value right here of 1. Let's pick another point. Like, let's say we pick a point right here at like 8, okay? Well, the reciprocal of 8 is 1/8. So as I get closer here, now I'm going to get smaller. I'm only going to be 1/8 instead of 1. So you could do that with every single point, but you're going to be seeing that cotangent is always going to be decreasing, right? We can see we must be approaching this vertical asymptote like this, continuing on into this little second square. If I had a point right here, that would have a y value of, let's say, -1. So if I reciprocate -1, I still get -1. If I pick a point way down here at, let's say, like -8, well, the reciprocal of that would be -1/8, which would be like right here. So we can see, even if we reciprocate those points, we're still creating a decreasing shape for cotangent. So it looks very, very similar to tangent, but each of the points is reciprocated. So that's going to be our cotangent graph. Where are the vertical asymptotes for cotangent? Well, our first one is right here at 0. And we're going to have one, again, another pi and another pi. So every single pi n, where n is an integer. Now technically we don't need to put the 0 out there in the front. Like, we can simplify this to just x equals pi n, where n is an integer. So we're going to have a vertical asymptote every single pi n for cotangent. Thanks for watching the video.